Hi! In this video, we'll talk about how we can actually evaluate integrals using symbolic or algebraic methods. So to recap what we saw before, when we see this double integral symbol, the integral of a function f over a region R, the way that we approached this was to first take our region and divide it up into smaller rectangles, then to choose a sample point in each of those regions, each of those subdivisions, and then finally we arrive at our estimate by taking each region, evaluating the function at the sample point, and then multiplying that by the area of the subdivision. We add all these up, and that gives us a total estimate. So for what's coming next, we'll make this a bit easier on ourselves by taking this delta A, that is the area of each of these small rectangles, and writing it as delta x times delta y. I think you'll allow that, right? The area of a rectangle is base times height. And then rather than picking an independent sample point in every one of these small rectangles, we'll just declare that all of the x coordinates will be the same. That is, in the first row, the first column, all the x coordinates will be the same. In the second column, all the x coordinates will be the same. And the same for all the rows and the y coordinates. And, well, as our rectangles are getting smaller and smaller, it really doesn't matter anyhow. So this will make it a lot easier if we assume this. So then we can rewrite our estimate this way. This is including everything we had before, where this innermost sum is corresponds to adding across the rows, and the outermost sum corresponds to taking those rows and then adding them up from the bottom to the top. So if we look at this innermost sum, we'll think about the x direction. As this factor delta x gets small, that is, as we have more and more rectangles in the x direction, smaller and smaller, more subdivisions, we get a limit, as we do with a Riemann sum, that approaches a definite integral. In fact, this expression on the inside deals with a fixed y value. We're only thinking about a particular row at a time. So this is a legitimate Calc 1 Riemann sum. That is, this gives a single variable integral for the variable x, and we can think of it as the area beneath one of the cross sections. Remember, a cross section we get by fixing a y value, so that's a function of x. We can take the area beneath it. So we're sort of doing some filing across each row. We can take this integral, or take this limit, which gives us an integral, and then we can take all those rows and add them together. And that's what's happening in the y direction when we then sum over all the k's, that is, sum over all the columns. And so this leads us to what's known as Fubini's theorem, which tells us how we can evaluate this double integral using what we'll call iterated integrals, one after the other. So if we wanted to evaluate an integral over a rectangular region, that is, x goes from a to b and y goes from c to d, we can just put one integral inside of another. We'll put the integral of f going from a to b with respect to x inside of an integral with y going from c to d. It doesn't matter which order we do it. We could do the other order as well. Put the y bounds and the dy on the inside, and the x bounds and the dx on the outside. So let's see how this plays out. We can compute this integral, the function on the inside, 12 plus x minus 3y squared, over this rectangular region. X is going from 0 to 2, y is going from 1 to 2. And Fubini's theorem tells us that we can write it this way. We have x bounds and dx on the inside, y bounds and dy on the outside. And for the moment, let's ignore those y bounds and that dy. We'll approach this integral with respect to x on the inside the way we would in a Calc 1 class or Calc 2 class when we do integrals. With one exception, there's a y floating around in there. But just like we do with partial derivatives, as far as x is concerned, y is a constant. So we treat it that way as we do our antidifferentiation. So we can take the antiderivative, we can plug in the endpoints, and when we're done, there are no more x's. We have just now a function of y inside of an integral with y bounds and dy. So we can do it again. Take the antiderivative, plug in the y bounds, and we get the answer is 12. So here we applied the fundamental theorem of calculus twice, that is the single variable fundamental theorem of calculus. And we used the method of iterated integrals, that is we did one integral at a time. We evaluated the inside integral, and then we took the result of that and evaluated the outside integral. Let's take a look at Sage and see what this process sort of looks like. So here I have the function f defined to be 12 plus x minus 3y squared, the same one we saw in the video. Here's a graph of that function over this region we looked at. And remember, the idea behind the iterated integrals was that we sort of integrate across one direction first, across the x direction or y direction, and then we kind of collate them. We add all those together. So that's the idea here. We take our surface, and what I've done is I split it into, let's see, 7 strips. So we can imagine there's 7 rows on the table, and we integrate across each of those. Well, integrating across each of those is just like integrating a cross section. So we have 7 kind of single variable functions, each one involving x, and then we can add those together, these sort of strips, the volumes of each of those. And as we take more and more, these strips get thinner and thinner, and we get our double integral. So if instead of 7, I used 40, so maybe it's too many to see anything. So you can sort of see how it's jagged here, but these kind of plies fit together to give us the volume of our surface. So this was integrating in the x direction first and then sticking these together in the y direction to get the volume. We could have done the opposite. If we integrate in the y direction first, that's like integrating across these cross sections and then sticking them together in the x direction to approximate the volume of the whole surface. And as these kind of bands get thinner and thinner, and there's more and more of them, then we get a better and better estimate of the surface. And we can check, I'll show you how to do this in class, that the actual value of the integral is 12, as we saw. So there's one more example here. Try this one out. I'll show you the answer in the next video, and then we'll talk about how we can use this method of iterated integrals over regions that are not rectangular.